All right, today we're going to talk about gases. So when we talked about phases or states of matter, we talked about the kinetic molecular theory. Remember, we called it KMT. So remember, the kinetic molecular theory attempted to describe states of matter based on the attractive forces between molecules and the kinetic energy they hold. So the kinetic molecular theory has been widely used to explain gases. So we'll just talk about that a little bit. All right. So according to the kinetic molecular theory, right, important things, all gases have mass, right? But the molecules are very far apart. Remember, because the kinetic energy is greater than the intermolecular forces that would attempt to hold the molecules together. Right. So since that kinetic energy is greater, they don't hold on to each other. They're constantly traveling apart. Right. Because of that, gases can be compressed, and they have very low density. Because remember, density is mass over volume. Okay. So gas particles are constantly moving at a very rapid rate. Right. Because they have that kinetic energy, and we'll talk about it down there. But kinetic energy is equal to 1/2 the mass times the velocity squared. So, but you can't change mass. If kinetic energy is increased, this velocity to a power 2 is increased. So if I double the energy, I quadruple the velocity. All right. So that explains why they fill their container. Right? We already said that. They move in a straight line until collided upon. Right? And they freely diffuse. So this word diffuse means to mix. So gases will mix to form solutions. And if you learned in the other semester of chemistry, solution is an evenly mixed component of things, which particles are too small to be seen and does not separate normally. All right. And the last thing is the collisions are said to be perfectly elastic. And elastic means there's no loss or gain in energy. So because the gases are colliding into each other, they leave with the same velocity, right? This is velocity again, that they came in with. All right. That's what elastic means. Right there. There's no loss of kinetic energy. But this also explains the expansions of gases will heat it. If I add more kinetic energy, add more velocity in the same period of time, gases are farther away from each other. So those are the basic properties of gases. So for the most part, we'll talk about gases in closed containers, but atmospheric pressure you have to know about. All right, so atmospheric pressure, here it is right here, is the result of the mass of the molecules and the gravity of Earth. So if I look at this picture right here, if you were sitting right down here on the Earth, atmospheric pressure is the sum of the mass of all the gas standing on top of you from you to the top of the atmosphere. Right? It's actually pretty significant. Right? I think it's about 12 pounds per square inch. So that gravity, that air pressure is due to mass, and that air pressure at any point in the atmosphere is in all directions because the molecules are moving in all directions. All right. So a couple things you need to know. The reason why this slide was important is you need to know the pressure of gas at sea level. Right. So we use sea level at the point where the ocean meets the land as a standard for pressure. And these values here you'll use in all your gas equations. 760 millimeters of mercury. And that's the standard because originally we measured atmospheric pressure using a mercury barometer. And it was essentially what a mercury barometer is. It has a dish here. And mercury sits in the dish. Remember, mercury is the only metal that's liquid at room temperature. It's a very dense fluid. And as the atmospheric pressure pushes down on this reservoir, it raises mercury up a vacuum tube. And if this was at sea level, that mercury would rise up about 760 millimeters. Right? So that is called 1 atmosphere. Right? In chemistry, we use the unit kilopascals. Right. So you'll see kilopascals a lot in chemistry problems. But those are all attached to your homework is an equation sheet, and on the equation it has these here. Now the only thing it might say difference, instead of millimeters of mercury, there's a unit called a torr, which simply means millimeters of mercury. Okay, if you see that later. All right, so gas variables. There are 4 gas variables we use to calculate all the stuff with gas. I'll just go over those quickly for you, because we have a second video we need to talk about. All right, so the first, N, is the amount. So this is the amount in moles. So if N equals 1, that equals 1 mole. Right? If it equaled 2, that equals 2 moles. All right. So N is the amount of gas. So we can equate everything to pressure. So we're going to go to a closed system now. So closed system. So pressure is created by collisions. All right. So if we look at here, if we had a box and we had molecules, remember kinetic molecular theory says molecules are moving in a straight line until they hit things. Collisions on the wall of this box is what creates pressure. So if I double the amount of gas, I double the amount of pressure because there are more collisions per unit time on the wall. So pretty simple. Next gas variable is volume. So the volume of the container matters as well. So usually volume is measured in liters, but for most problems you can use milliliters, decaliters, kiloliters, but liters is the base unit that we use for most stuff. But you can use anything. You can use gallons, quarts, doesn't matter really. All right, so here we go again. So if you look at this picture down here at the bottom, I'll increase it for you. If I have gas molecules in here, they're moving and they're colliding. Right, and that's creating the pressure in here. If I squeeze this volume down like in a piston, right, so now my gas molecules are all hitting really fast. So I just increase the amount of collisions per unit time, right? Oops. Let me make this a little smaller again. All right, so if I decrease the volume, I increase the number of collisions per unit time. All right. Temperature. So temperature is one we have to think about. So temperature represents kinetic energy. Right? So if I increase the temperature, which is the average kinetic energy in a substance, I increase the velocity, and I get more collisions per unit time. So, but everything needs to be converted to Kelvin. Right? We convert it to Kelvin because there are no negative numbers. All right, so we use Kelvin. Here's the conversion per Kelvin. It's on your formula sheet as well, if you forget it. But if you get a problem that has Celsius listed, you have to change it to Kelvin because you only get the right answers for Kelvin. But again, if I have molecules in here and they're colliding with the walls, if I heat the temperature, they just collide faster, right? And they increase the pressure. And then the last is pressure. Right, we've been talking about all along. So pressure, make sure you know this, is created by collisions, right, on the walls of the container. Pressure kind of ties in all the other variables. Here's an important one to remember. It's directly related to the moles. If I double the amount of gas, I double the amount of collisions. It's inversely, right, related to volume. If I double the volume, I halve the pressure because it takes twice as long for the gas molecules to collide. And temperature directly. If I double the temperature, my velocity goes up, I double the pressure. Okay. And the last is standard temperature and pressure, often called STP. We talked about that when we talked about moles, right? Still the same thing, right? The values for this, right, 273 degrees Kelvin or 0 degrees Celsius, and then 1 atmosphere of pressure, which remember is 101.3 or 760 millimeters of mercury, or torr if you see the word torr. All right, that's it for this short one. We'll see you shortly with the other one.